Come on. There. Okay, so where we quit last time, we kind of just talked about some really basic kind of like old school or high school definitions of just what is chemistry, what is matter, what is energy, how energy kind of can change forms. So the next big sort of part of this is the fact when we talk about matter, we said matter has two characteristics. That means that it is anything that, what? Has mass and takes up space. Okay, so those are anything that you can think of. If it has mass and it takes up space, then it is included in matter. Remember that that can then be a solid, a liquid, or a gas. Those are just different states of matter. They vary by how the particles are arranged, whether they have a defined or an indefinite volume and shape, and then also like their amount of energy, like how much vibration they have. That's going to determine, can they fit up real close together, or do they end up spacing themselves far apart like gases because they vibrate so quickly? Well, we can take matter though, and we can define matter basically as to what its makeup is. So if we have different substances that are physically mixed together, that is the definition of a mixture. Okay, so a mixture is two or more substances that are physically combined. Okay, so physically combined means that I could separate them. Sometimes it might be kind of complicated to separate them, but in theory, I could separate them back out. So you just think of, like in your head, like just think of like the M&Ms. They've all got different colors, right? So you could sort them. Sitting in a bowl, you can tell that there are different colors and you could sort them. So that's kind of a really simplified idea of a mixture. Two or more substances that are physically, and that's the kicker, physically combined, which means I can separate them. And when I separate them, those substances will have characteristics separate from each other. So they're not still going to act exactly the same. Pure substances, on the other hand, cannot be separated into different components. Pure substances all of their smallest units are the same. I cannot separate pure substances into smaller components physically. I might be able to separate them chemically, but I can't just separate them by size, or separate them by color, or separate them by layers. I can't pick out any differences. If I take a pure substance, so if I have like a block of a pure substances and I split it in half, those two parts are going to be alike. If I split them in half, same thing. I could go down all the way down to the smallest particle size, physically splitting it, they would still all have the exact same characteristics. So you see sort of the difference between them. Okay? So mixtures. Mixtures can either be homogeneous or heterogeneous. And here, there's a lot of times in this class, I'm going to kind of tell you like what a word term is. So a lot of them are actually Latin terms or Greek roots and such like that. You'll find the same thing in anatomy and physiology. So a lot of times that can like help you to remember, okay, every time I hear this, like osteo, then I know it's bone. Okay? Every time I hear myo, I know it's muscle. Okay? So in this, if you hear homo, homo means the same. Okay? Hetero means different. So anything that is going to be homogeneous means it's going to look uniform. So homogeneous mixtures, when you look at this mixture, you can't see layers and particles. They're there. You could technically separate them back out, but it's going to look uniform. And you sometimes have to know something about the mixture to be able to know that it's actually a mixture, like cake batter. So once you get done blending cake, yellow cake mix, you add eggs, you add oil, you add water, you add the cake mix, you blend it for 2 minutes. When you look at it, does it look uniform? Like even if you look up close, it's just all yellow, right? So it's a yellow liquid, so it looks uniform. But you know that you put stuff in there and physically mixed it together. So that's a good example of a homogeneous mixture. If it sits, it doesn't separate back out. It still stays that uniform appearance, but you know its composition is made of other things. Whereas a heterogeneous mixture, this is where you have something that you can see layers. So the M&Ms example, that is an example of heterogeneous mixture, okay? In fact, every M&M is a heterogeneous mixture as well, because if you like cut it in half, you can see the candy coating and the chocolate inside. So you can physically see that there's different parts to it. So that's just sort of a very simple idea. If you take a scoop of dirt, okay, that's a heterogeneous mixture because you're going to see small little pebbles in it. You might see little sticks. You might see like sandy material, different colors to the dirt. So you know that that's a homogeneous mixture. So seeing those different layers tells you that it's a combination of them. Okay, so remember hetero means different. Homo means the same. Now in a pure substance though, all of the particles are the same. You can split this though by defining what those particles are. So if you have a pure substance and it's an element, then it's going to be on the periodic table, okay? So I gave you the name of the 30 that you need to learn. So for the first exam, you need to make sure that you know the names and the symbols of the 30 that I gave you at the very end of class. Okay, so that's like elements 1 through 20, and then those other 10 that I gave you as part of the list. So that's really the easiest way. If you see an example where it says like a bar of gold, okay? So if you see gold, then you look up there and you're like, oh, gold is AU, it's on the periodic table. I know that that's an element. So if I have pure gold, or if I gave you chlorine gas, because you can see, just pick a spot. I think there's no empty spots. There's no like defined seating in there. Okay, chlorine gas. So you look up there, oh, I see chlorine on the periodic table. Okay, and I see chlorine all by itself. So therefore, I know that that's an element. Okay? But a compound is where I have 2 or more elements that are chemically combined. So you will always see a chemical formula and it will have more than one element in the list. So a compound has 2 or more elements, and the difference between a compound and a mixture is a compound, I can't physically separate a compound into different components. So for example, if you see NaCl, so from the formula, Na is sodium, Cl is chlorine, but seeing those written together, NaCl tells me that I have 1 sodium and 1 chlorine atom, and they're chemically combined. Okay? H2O. So H2O tells me that there's 2 hydrogens and 1 oxygen. So notice if there's only 1, they don't put a 1 after the element. Okay? So they have these funny rules that they just don't put this, but they do put that. So 1 in any formula, if you see an element symbol but nothing after, then just remember that means that I've got like 1 of each of those. 1 of these and 1 of those. Okay? They're just not going to put the 1, but that's going to tell you what it is. Whereas if I see H2O2, that tells me 2 hydrogens and 2 oxygen. So the number after the element always tells you the number of that element in a single molecule or particle of that substance. Okay, so H2O, water. So if I asked you one and I told you water, I would give you the formula as well so that you can kind of like put yourself a note. Like with a compound, you're going to see a formula and you're going to see more than 1 element in that formula. So some of them can be pretty small, like H2O. Some of them can be much bigger. So like if we're talking about sugar, talking about glucose, C6H12O6, that tells me there's 6 carbons, 12 hydrogens, and 6 oxygen in 1 molecule, in 1 particle of glucose. So the easiest thing to do with these is let's try a couple of them, right? So let's see if you can tell me some of the simple ones that you've probably come in contact with. So like Gatorade. So first off, if you know that Gatorade, it has mass, it takes up space, so therefore it's matter. So we can classify it. So would you say that it's a pure substance or a mixture? It's a mixture, okay? And again, you know that because then when I said Gatorade, you started thinking about, okay, like there's the red one, the orange one, the white one, right? So you start thinking about all the different colored ones. And then you start thinking about the advertising they've done because they tout that as being like, this is what you drink after you exercise because it helps to replace your what? Electrolytes, right? So because of advertising and everything, so that's something, it's familiar. Sometimes you need more information, but a lot of these are going to be like pretty quick. Gatorade then, you know that this one's a mixture. So then the next question, if it's a mixture, you define it then, is it uniform or can I see layers, parts, and pieces? Uniform, so that means it's homogeneous. It's a homogeneous mixture, okay? So if it's a mixture, you don't worry about defining it by elements or compound. If it's a mixture, it's just homogeneous or heterogeneous. So what about chocolate ice cream? So you like open the container, look at it, what would you say? Mixture. Okay? And so that one, like if you have to like, some people are like, I don't know what's in chocolate ice cream. Well, pretty much it's just cream, sugar, and cocoa. Like if you don't have all of the weird stuff that they like to put in ice cream, that's pretty much like original ice cream. That's all that it was. Is it homogeneous or heterogeneous? Yeah, so if you take off the lid, it's just all brown, right? You don't see any parts, pieces, or anything like that. So it looks homogeneous. But then what if we're talking about chocolate chip ice cream? That's still a mixture. It's ice cream, right? Still is going to have that cream, sugar, and then this probably has vanilla flavoring in it. But you can see little black flecks. So now I can see parts. So yes, it's still a mixture, but now it's hetero. Okay? Because in theory, I could go pick all those chocolate pieces out and like separate them. That would be strange, but you could do that. Sometimes you need a little more information, so I will tell you what distilling is, if you've never thought about it or if you've never had anything that's been distilled. So to distill means a means of purification by boiling. So you can take tap water, so you could just get like a gallon of water, you can put it on the stove, you can boil it, and you'll start to get steam. So when you distill water, you boil the water, the steam comes up, it actually gets diverted into a tube where there is a chiller on the outside. And so what that does is it cools the steam. So when steam gets cooled, what happens to it? It goes back to being a liquid. So it condenses. So it condenses back into a liquid, and then you collect it. So the boiling point of water, which is about 100 degrees Celsius or 212 degrees Fahrenheit. So that boiling point is much lower than the boiling point of the other stuff that's in your tap water. So like the chlorine that might be in there, any ions in there, any salts that might be in there. So there are always like trace amounts of other things just in tap water. But now in this distilled water, all that stays behind in the boiling flask. And what I collect as distilled water is now pure water. So what would that be, a pure substance or a mixture? It's a pure substance. And from looking at it and the name, is it an element or a compound? It's a compound. So if I gave you an example like that, I would give you more information. If it was something that we haven't already talked about, something that you're like, I don't know what this is. Okay? But tap water, so we started off talking about tap water, right? So tap water, what is that? It's a mixture, right? So tap water is not pure distilled water. It's a mixture. Even though 99.9% of it is water, there's still maybe that 0.1% where they've chlorinated the water as a way of trying to disinfect it so that it's safe to drink. They may be salts that weren't filtered out in the water treatment plant. There may be metals. Sometimes metals will actually leach out of the pipes that transport the water all the way to your tap. So, can you see that? Like when you pour water into the glass and you sit and look at it? I hope not. There have been times in Wilson when I was like, oh no. I think in August, sometimes the smell, I was like, I ended up putting a filter on our kitchen sink because I was like, I can't drink this. Like, it just looks like it came out of a swamp. I don't know. But in theory, it really should be homogeneous, yes? Okay? It should look uniform. If you live in Flint, Michigan, if you live in Spring Hope, anybody in Spring Hope? They have actually had a boil water alert 3 times in the last 6 weeks. Yeah, and Spring Hope is like 50 miles down the road. Okay, they have had a lot of issues with their water supply. So, people think it's like only big places, but no, even small towns can have water treatment issues. So just be glad you're not a Spring Hope person if you don't. All right, so I have a couple more. I'm going to give you a minute. You can talk with your lab partner or your elbow partner, I guess. You can look at the other person. You can talk across. That's fine. First column, I want you to look at each of the items, identify it as a pure substance or a mixture. That goes in the first line. The second line, if it's a pure substance, tell me if it's an element or a compound. If it's a mixture, is it homogeneous or heterogeneous? Okay, so just jot those ones down, and then we'll run through them. And if there's ones you're not sure of, you can leave those ones blank because we will talk about them. So maybe some of them you got real quick, some of them you're like, I'm not sure, okay? And some of them you may need a little bit more information. First one's pretty straight. NaCl, what would you say? Pure substance. And based on this, it's a compound. CMPD. Good? Okay? Second one, and you know this because one, all you see is a formula, and you see Na and you see Cl, right? So if that's all you get and you have a formula, then you know it's a pure substance and it's a compound. Second one, 10 karat gold. Well, you look up and you're like, well, gold, but what the heck does 10 karat mean? So pure gold, you could bend. Pure gold is really soft. So you can't make jewelry, you can't make utensils, you can't make stuff out of it. You have to add other metals. So they add metals. I was actually looking it up to be sure I knew exactly which one. So they add silver, okay? So they'll add silver to it, they add nickel to it, and they add zinc to it. Okay, by adding those, they add them, heat it up, and then when it cools, now it's hard. Okay, well that's silver, so that doesn't do anything. Okay, so now it's hard, and so now you can shape it. And now it'll maintain its shape, and because if you had pure gold and made earrings, they would just like fall off. Okay, so you can have 10 karat gold, which is really kind of the lower end amount of gold. You can have 14 karat gold. The biggest you can have is 24 karat, has the highest amount of gold. Anything higher than that, it's just too soft. So that's what that means. So now knowing that, what is this? It's a mixture, right? So because I know that it has gold in it, it also has nickel in it, it has silver in it, and I know that it also has some copper. Copper? No, zinc, that's what I thought. All right? So it's actually a combination of those metals. And the carat is really telling you how much gold compared to the others. The higher the carat, the higher the percent of gold, but you reach a maximum. You can't really go above 24 karat where the gold's just too soft. So we know this is a mixture, but now if you look at something like a 10 karat gold ring, does it look homogeneous or hetero? Homo. All right, so what about salt water? Mixture. Anybody have a question with that? Everybody got that? And again, kind of like the Gatorade, you got to think in your head, okay, salt water. Okay, so it's water, and you put some salt in it and stir it up. Okay, so homo or hetero? Homo. Oxygen gas. It is a pure substance. Okay, oxygen gas, pure substance. Is it an element or a compound? It's an element because you can see just oxygen by itself on the periodic table. So you always see it listed as O2. it's an element, even though there's 2 oxygens per particle, it's nothing but oxygen. So that makes it an element. Now, unstirred paint. So if you go to Lowe's and you buy paint straight off of the shelf and you don't have anything added to it, and you bring it home and you open it up, what do you see? Yes. So there's like a clear liquid layer on top. Now, if you get Lowe's to add color and they shake it, well, that's going to change how it looks when you get it home. But if you've had like a can of paint sitting in the cabinet, because like I keep mine in the closet, like, you know, after 3 months and you open it up, it's not just all mixed, even though it was shaken. If it's unstirred, it's a what? Mixture. And you would describe it as being hetero, because you can see that layer. It's going to separate. And you got to stir it to make it become homogeneous.
So is like the homo and hetero stuff, is that just like
what it looks like when you look at it.
When a person looks at it.
Mm-hmm.
Okay, because I was
Okay.
a little bit confused about that.
Yes. So like really, and really it's a suspension. So we'll talk about mixtures again in chapter 8. So a suspension is when you have stuff that doesn't really mix completely, but when you shake it up, it looks mixed, but it'll always separate out.
Okay.
You know, like dirt and water. Like if you have dirty water, it can look uniform, but if you leave it, all that dirt settles out and you can see clear liquid and then solids down in the bottom. So it kind of depends on its condition. So that's why I would give you something like this as an example. So if I said stirred paint or shaken paint, then you would say it's homogeneous. Okay? It looks uniform now. It doesn't necessarily mean it's always that way, but the condition you have it in now, it's going to look uniform. So ammonia, does anybody know what this is? It is a pure substance. So in this, again, sometimes you need a little more information. So I wouldn't just tell you ammonia, because that's one that's not necessarily something everybody knows off the top of their head, but the formula for ammonia is NH3. So if I have ammonia, it is a pure substance, and that makes this a compound, because I have nitrogen and 3 hydrogens per unit. What about air? The air in this room. It's a mixture, okay? And it's a mixture of gases. Air is roughly 79% nitrogen, 21% oxygen, and very small amounts of a lot of other stuff, okay? Very small amounts of water. Now in the summertime, it might be a lot more humid and there might be a higher water content outside, especially in eastern North Carolina. There's a very small amount of carbon dioxide. The more people in the room, the more carbon dioxide levels there would be. So there is variation. There's small amounts of some of those noble gases like argon in the air. But just knowing these are the 2 components tells you it's a mixture. And so again, you would need some more information. Maybe you knew this, maybe you didn't. So if it's a mixture though, the air in this room, homogeneous or heterogeneous? Homogeneous. Can't see it, right? It's all uniform. Now, when it's foggy out, there's enough water condensation vapor in the air that you can actually start to see layers, but that's not what the description is. Asphalt's the last one. What do you know about asphalt? It's a mixture. So what's in asphalt? Rocks. Haven't you ever watched when you're driving by and they're like tar. God bless, I don't know how they can do it. Because it is like so crazy smelly and hot as blazes when they're like, that big machine thing is going on laying the black, and they're just out there, doo, doo, doo. I'm like, driving past them, I'm like, I don't even know. Pay them more money, because I ain't doing that. Rocks, tar, anything else? There is sand, okay? Because if it was just rocks, it'd be very bumpy. So the sand helps kind of do some filling. In fact, they even push crushed up glass in the roadbed. Did you know that? Yeah, some people are like, what? Why? That would like eat your tires up. Actually, what does it give you? Reflection. So it actually allows like your headlights bounce off the road better, and it actually allows you to see a little bit better at night. So it's not a lot and it's finely ground, but that glass is going to give you a little bit of reflection off of the road. So now you know this is a what? No doubt. Now, if you go up and you look, when you go out into the parking lot and you look at the ground, what are you going to tell me that is? Hetero. Because you should be able to see little rocks, little differences, layers. Okay? So hopefully that helps. So you have a dynamic study module that's due Sunday night in Mastering Chemistry. Remember, if you don't have the access code, you still got a 2-week trial. So you can go ahead and get started on that. That dynamic study module is called Understanding Matter, and it's going to ask you questions about mixtures, pure substances, solids, liquids, and gases, characteristics of matter, all the things that we've just kind of talked about. So you should find this just to be a good review, and that's the reason why I assign these like the Sunday after we cover it in lecture, because I want you to go through and do it, within a few days of covering the material, just to help reinforce it. Okay, so just put yourself a little note if you haven't worked on it or haven't looked at it yet, just remember that's what we've got. So all these elements, when we're talking about the simplest of the pure substances, so all these elements, they're listed on the periodic table. In the periodic table, if you've got your handout from last time, you might find it handy to go ahead and pull out your paper periodic table. So the one that is identical to the laminated one, I gave you a copy because now you can write on this one, right? So you can add notes, you can add information, and you may find that that's going to help, especially if you're a real visual person, like seeing the periodic table and adding things to it, that will help. You may want to go in, you could color in the ones that you need to remember. You got to know 1 through 20, but then we've got that other list that's on the next slide, so you'll see it again anyways. So you could color those ones in. Just general information, the periodic table, you will always have it when you take a test. So you don't have to memorize anything on the periodic table. You have to learn what the periodic table will tell you, because it actually tells you a lot. We will use it a lot in these first 3 chapters, because you can figure out protons, neutrons, electrons, you can figure out atomic mass, you can figure out named symbols from names and such. So general stuff, 1, you have the columns. So the vertical columns, they're arranged purposefully, so it's not random. They didn't do it just to fit it all on a page. So it's actually set up so the vertical columns are always arranged by similar elements. They're called groups, and they all have similar properties. So for example, the very first column, hydrogen, lithium, sodium, potassium, rubidium, going down that first column, those are all called the alkali metals. And they found that they have very similar reactivities, like they react with oxygen in the same way. They react with water in the same way. They are all solids, their size, even their atom structure is similar. So that is why they are all grouped in that column. Going all the way over to the far right, does anybody know what those were called? Helium, neon, argon, krypton, xenon, radon. Those are the trivia question. The noble gases. These are the noble gases. So the noble gases were named that way. They were also sometimes called the inert gases. That's another way that they've been termed. The noble gases were actually some of the last elements discovered because they're not reactive. They're extremely stable. So this is the last column on the far right. They are very stable. They don't form compounds. Well, some of the big ones do, like xenon will, but we're not going to work with that. Okay? For helium, neon, argon, they don't form compounds. So they are so stable, they just exist as an element.
And they're not reactive.
They do not form compounds. So that means they do not chemically combine with other elements. They exist as a stable element all by themselves. So that's where they were noble, because they didn't have to interact with anything else.
Are those the ones on the bottom? Is that what you said?
Nope, going down this is columns. So we're looking at the group, the vertical columns.
Okay.
The ones right next to them go in 1 from the right. So that is FCl, Br, and I. Fluorine, chlorine, bromine, and iodine. Chlorine. What do you know about chlorine? What do you see chlorine in? Pools. Okay, so chlorine's put in a pool. Why? Keep it clean, right? It's antimicrobial, right? So that's going to keep any bacteria, any fungus, anything from being able to grow in your pool. If you've ever been in a hot tub, they use bromine tablets as a means of a disinfectant for a hot tub. So it's typically like a little white tablet and it just sort of floats. So it does the exact same thing. So bromine can be used in very small bodies of water compared, you wouldn't want to use it. It's too expensive to use in a really big swimming pool. So instead, they'll just put it in things like a hot tub. Iodine. Where have you seen iodine? What? Clean what? Yeah, so it is a surgical scrub. Okay? So when they took the cast off of my leg, my entire leg was orange. Okay? So then I was like sitting there, I had my little bath wipe, and I was scrubbing them, and like the bath wipe turned orange, and I kept scrubbing it, trying to get it off. Why? Why do this? So it's betadine is the most common iodine scrub that's used. And they will scrub, I was out, so I don't remember it because they gave me the juice and they were like, see you later. Okay? But they literally will sit there and scrub your leg for 5 minutes with iodine. Because what does it do? It has the same characteristic as chlorine and bromine. It is a antimicrobial. It is an antiseptic. Okay? So it decreases the number of living microbes on the surface of the skin, and that's going to reduce the risk of what? A surgical infection, okay? So if we make sure we decrease the amount of microbes there, then when we now have to cut you open and you've got this open wound, that decreases the chance that anything is going to end up getting in there. And again, I didn't have any problem, and I've had 2 surgeries now this year on the same leg, okay? But same thing. So iodine for a surgical scrub. So it is a skin antiseptic. They can use fluorine, but fluorine is really expensive and it is somewhat explosive, okay? So it is very reactive, so not usually used, but it could be used for the same thing. That is that entire column then. They have this characteristic. Fluorine, chlorine, bromine, and iodine all have an antiseptic, antimicrobial property. So that's why they started arranging them, seeing, oh, these are similar, these are similar. Oh, these are similar. Look, they fit. They actually line up and match. Copper, silver, and gold. Those they called the precious metals. So gold and silver, you always associate like with jewelry and like, you know, like higher end jewelry and types of things. But now, right now, you go buy copper at Lowe's. Copper has quadrupled over the last couple of years because they like slowed down mining and everything else with COVID. So it is crazy expensive. So expensive that people like break into houses and cut copper pipe out of walls. It's like, it's insane because of how expensive that copper metal is now. So all 3 of those in the same column, Cu, Ag, Au. So those, just remember, so things that are in the same column are going to tend to have similar properties. And we'll actually talk about this again because it really rolls back to they have very similar atom structure, okay? Now, one's going across. So going across, they call that the period. So like hydrogen to helium. So what do you notice going from H to He? So looking at it, what would you say happens if you compare H and He? What's different? The number above, what happens? Goes up by 1, right? So going left to right, the number goes up by 1. If you look at the next column, see that Li and Be, or sorry, next row, Li and Be, then over to boron, carbon, nitrogen, oxygen, fluorine, and neon, going across, do you see that that number increases by 1? Okay, so looking at the periods or the rows going across, you see that there is, the number increases by 1. That is the atomic number, the number above the symbol. But the atom size also increases as you go across. They don't increase by the exact same number. So the mass of the elements increase as you go from right to left. Left to right. So that allowed them to do this organization. The other thing that they found is in doing this, they actually ended up with all the metals on one side of the periodic table and all the non-metals on the other side of the periodic table. So if we look at the periodic table here, I like this one. We just don't have the color. And this one, everything that is blue, purple, blue kind of color, those are metals. So notice that they're all kind of to the left side. All of the ones that are non-metals are all the ones that are in yellow. Those are all the ones that are in that upper right side. And the divider line, it's not on this. They don't actually darken the little staircase thing, but you can actually look at your periodic table, and that's one of the reasons I like it, is your periodic table has this darkened, very technical, the zigzag line. That's what they call it. It starts under boron, and it basically zigzags all the way down. That zigzag line is kind of like the divider line. So everything to the left is going to have metal properties. Everything to the right is going to have non-metal properties. And the few that lay right along the line, they call those metalloids because they're kind of both. They have some metal properties, some non-metal properties. So those are the ones that don't just like fit into one category or the other. Sometimes they call them semi-metals. Metalloids is a pretty common term that they use now. So from looking at this, do we have more metals or more non-metals? Way more metals, okay? So now looking at that one and looking at this periodic table, everything that's in black is a solid on this periodic table. So that's kind of neat. Everything that is red is a gas on this periodic table. Everything that's blue is a liquid. So this one actually tells you solids, liquids, and gases by their color differences. So you would say most metals are what? Solids. See how everything, like on this side, all but one or two of them, they're all black. Okay? So far and above, almost all metals are solids. What about the non-metal corner? So look at the yellow where those non-metals are. You would say most non-metals are gases. Okay? So that's kind of like they saw that it's a state of matter. There's a difference between most metals are solids, most non-metals are gases. There's only two blue. Okay? So blue are the liquids. There is only one liquid metal, and it is one of your names and symbols. Mercury. Very good. Yes. Hg. Remember when taking blood pressure, mmHg, millimeters of mercury. So mercury is the only liquid metal, and the only liquid non-metal is bromine. And well, bromine, it's like right at like 75 degrees, it becomes a gas. So it's not liquid. It's only liquid at cooler temperatures, so it's sort of an interesting one. But yeah, so those are just as a trivia information that mercury and bromine are the only two liquids at room temperature. One's a metal, one's a non-metal. Now notice here, see the ones that look in white? Like that always kind of throws people like, well, what is that? Like if we have solids, liquids, and gases, what's the white ones? Well, the white ones are actually radioactive isotopes. So they are unstable atoms that are like artificially made in a laboratory. They don't last very long because they're so unstable. So they've like taken atoms, smashed them together, made them merge, and made this element, but then it breaks down. So it's really hard to study something that's like that because you're like, it's there, it's gone. It's there, no, it's gone. Okay? So because of that, you really can't, you'll notice like the numbers underneath are in parentheses because you really can't define their mass as much. They know they exist and they have some chemical characteristics they know, but a lot of them they really don't. Okay, so those are ones, just because of that, they don't really define them as a solid, a liquid, or a gas because they don't last very long in the atmosphere. So as soon as they start breaking down. It's because like chemists like to do stuff like that. Let's make stuff, yeah. Okay, so again, here is your list. These are the only ones that I expect you to know the names and the symbols for. All elements 1 through 20, and by number, the number above each of the symbols is what we talk about, the elements by a number. So hydrogen is 1, helium is 2, lithium is 3, beryllium is 4. And then remember I showed you last time, if you go to your e-text, and you go all the way down at the contents, like go all the way below chapter 12, you'll see it's not an appendix. Back matter is what they call it. Like, it sounds very strange. It's another word for an appendix. Down at the very bottom, you can see the periodic table, and they have a list of the elements alphabetically. So that'll give you like the spelling. So that way, if you want to double check spelling of beryllium or phosphorus, so those ones can sometimes be a challenge for people to try and spell correctly. So if you want to check those, that's in that back matter section at the very end of the e-text. Then you've got the extra 10. So chromium, iron, cobalt, copper, zinc, bromine, silver, gold, mercury, and iodine. Those ones you need to know the names and the symbols. So if I give you the name, you should be able to give me the symbol. If I give you the symbol, you should be able to give me the name. Any other elements we talk about, I will give you the name. So like we're going to talk in the next chapter, we're going to talk about radiation. So we're going to talk about stuff like plutonium and uranium, but I would always give you the name and the element symbol. I would not expect you to just memorize those. These are the 30, okay? So if you want, you might want to make a list. Some people do them like, like test themselves, like write the names on one side, symbols on the other side, and just practice it until you can get them. Do note that if there is 2 letters to the formula, to the elements notation, the first letter is always capitalized, the second letter is never capitalized. And that way you can tell that this is cobalt, capital C, little o. Don't make the mistake of doing CO because that's actually carbon monoxide. So that's carbon and oxygen. So if you see in a formula capital letters, every capital letter represents a different element in a formula. Okay? If you see lowercase, and I'll tell you one of the ones, in this one, I know that there is no L. There is no element that's just L, but I see people do chlorine and they like to capitalize C and L. And I will tell you that I see this, I can't tell you how much. That's Florida, okay? FL is not fluorine, okay? So make sure you remember F, just F by itself, because I see that every semester. And I'm always like, that's Florida's abbreviation. That's not actually an element, okay? All right, so a couple other things about metals and nonmetals. So we said characteristics of metals. 1, there's a whole lot more of them. There's fewer nonmetals. 2, metals are mostly what? Solids, liquids, or gases? Solids. With the only example of really being mercury. Technium is one of those unstable small ones. Nonmetals tend to be gases. So not all metals, but many metals, you can shape them. Okay, one of the things like being able to extract certain metals out of the ground, heat them, shape them, really made a huge difference in making tools, being able to make hammers, and being able to really like do industry and build stuff. So these are shapeable. Metals tend to be shapeable, bendable. Some metals, you can draw them into a wire. So like as copper is cooling, you can take copper and just start pulling on it, and it will stretch out so that you can make different thicknesses of wire. Then that was discovered that not only can you pull it into a wire, but what can copper do? It conducts. It can conduct electricity. So you can pull it into a wire. And these then made them conductors. So metals tend to be conductive. They can conduct electricity. Nonmetals, on the other hand, they're almost the opposite. Okay, so 1, gases are not shapeable. Remember we said that gases take the shape of their container? So if you're looking at any of the red ones, nitrogen, oxygen, fluorine, and chlorine, you can't do nothing with them. Okay, but if we look at like carbon, phosphorus, sulfur, see how those are black? So those are solids. The few nonmetal solids are very brittle. So for example, like black, like charcoal, like a charcoal briquette is mostly carbon. Can you shape that? Can you stretch it? Can you bend it? No. If you try to do that, what happens? Like if you took a charcoal briquette and you hit it with a hammer, what would happen? Yeah, it would just break into teeny tiny pieces. They say it's very brittle, so you can't shape it. So it's not shapeable. In fact, they found that nonmetals had a characteristic of being an insulator, not a conductor. So nonmetals don't conduct electricity. They're non-conductors. But this actually gave them a role of being used as an insulator. So you can put a nonmetal between two metals and it will block electricity from going from one part to the other. So this understanding and the sort of revolution of making extremely thin wires has led to the computer chip industry and has allowed, so like back when I was a kid, there weren't any computers. Well, there were like computers, like government computers. And like, I don't know if you ever watched like really old TV where they would have like a bank of computers, all these funny little wheels and lights would be flashing, beep, boop, beep, boop. But it was like this huge wall of computers and it was one computer. And like, it used like little punch cards. It was like super basic, like really crazy when you think like, I can't believe that people actually built stuff. Those all had actual wires, like what you would wire your house. But then they started to discover, hey, wait, we can take these nonmetals and like silicon, which is a metalloid, but it has this nonmetal characteristic of being an insulator. We can pull wires super thin, lay them in the nonmetal, and now the electricity will only pass through this super thin wire and not jump to another wire. So we don't have to have a rubber coating. We don't have to have a really thick wire. So computer chips, you know, they used to be like saltine cracker size. Now they're about a quarter of that, okay? Like your phone is a computer, okay? It doesn't have to take up very much space. And it was all this understanding of the differences between metals and nonmetals and being able to develop almost like this micro, they call it nano technology, because nano is even smaller than micro. So this extremely small circuits that they can use in order to produce very fast processing abilities. The metalloids. So the metalloids are kind of the in-between. There's not very many of them, and they lay right along that zigzag line, okay? Just remember that. So metalloids, they're kind of like a metal, kind of like a non-metal. They tend to be solids like metals are, but they tend to be less conductive like non-metals. So that's where that name kind of like was meant to be kind of like a hybrid of the two. That's a metalloid. It just has in-between characteristics. Just remember, don't do that.
So for the elements, we need to know 1 through 20 or 1 through 30?
1 through 20 and those 10.
Okay.
Okay? So chromium going down, that's 10. 2, 4, 6, 8, 9. And then iodine's 10. I didn't think iodine would fit all the way at the bottom, so that's why I wrote it up over on that corner. And the only reason I have these 30 is because we're going to talk about them over the semester. Okay, so it's not like I didn't pick random ones. I picked ones that you may actually see again and hear again. So being comfortable with those is a good thing.
What the symbols, the number on top?
So the atomic number, the number on top, we'll talk about in chapter 2 more about like what those numbers really mean and what they're allowing you to define. But you don't have to memorize the atomic number because you got a periodic table. Really, all you've got to do is you've got to make sure that you can tell me the symbol from the name from the symbol, and then that way you can use the periodic table to get the other information, okay? The zigzag line defines metals and nonmetals, so you should be able to identify any element by symbol as a metal or a nonmetal just by looking at the periodic table, but you always have that. And so that's the plus, and that's one of the reasons why I use the one that I use, because I like that it's really clearly defined as that zigzag line. So what's the application of elements in terms of living systems? Because yes, this is a chemistry class and we talk about chemistry for the love of chemistry, but I really want you to think about all of this and keep on applying it to living systems, health science, what your job is going to end up being. Whether you're taking care of 4-legged living beings or 2-legged living beings, doesn't matter to me, they're still the same characteristics. So when thinking about human or any living being's health, out of all, there is now known 118 elements. Out of 118 elements, there are only 27 found in the human body. Okay? So there are 27 of the elements found in the body. And they're not evenly distributed. So it's not like you have equal amounts of all 27. In fact, you have carbon, hydrogen, oxygen, and nitrogen. I affectionately call this CHM. Doesn't mean anything, but it's just a mnemonic: carbon, hydrogen, oxygen, and nitrogen. If you can remember CHM, then you can remember the main elements. CHM. Yep, just CHM. Right? Those four tell you 96% of the elements in the body are made of carbon, hydrogen, oxygen, and nitrogen. 96% of all the elements in the body. Huh? That's the next one. And those are, so if we, carbon, hydrogen, oxygen. So like carbohydrates are carbon, hydrogen, and oxygen. Proteins are carbon, hydrogen, oxygen, and nitrogen. DNA, carbon, hydrogen, oxygen, nitrogen. So all those biomolecules, your proteins, lipids, carbohydrates, nucleic acids, that is really where these come from. These are the really big building blocks that make up cell membranes, that make up your organelles, that make up the structures inside of the cell, that help to build tissues, that help to build organs. That's really carbon, hydrogen, oxygen, and nitrogen. Okay? But now that leaves us 24 elements, or 23, sorry, because we've only got, like, those other ones, there are 7. Whoop. See, now you're going to jump around. There are 7 that they call minor. So the main or major elements make up CHM. 7 of them are the minor elements. And all together, this is sodium, Na, magnesium, Mg, potassium is K, calcium, Ca, chlorine is Cl, phosphorus is P, sulfur is S. Those are your 7. Sodium, magnesium, calcium, potassium, chlorine, phosphorus, sulfur. These all together equal 3.9% of all the elements.
Are they all the minor elements?
Those are the 7 minor. So minor elements, there's 7. Main elements, there's only 4. So they list them as macronutrients. It's all the challenge of teaching anatomy and physiology versus talking to a chemist. Because I'm like, what? Nobody calls them that. Okay? They're the minor elements. And so those 7, they don't really make big building blocks. Well, phosphorus and sulfur do help a little bit. But most of these are what you think of when you think of salts, right? Your sodium levels, potassium levels, calcium importance. That they're more of your electrolytes, like when you drink in your Gatorade to try and replenish, is adding these types of things. So they're not so much the building blocks, but they have very important jobs. And so we will kind of talk about them when we talk about ionic compounds, because that's how these typically exist in. So that 11, so out of this entire periodic table, 11 elements make up 99.9% of you. Just 11. The small ones, these they call micronutrients. I call them trace. The trace elements. And there are 16 of them total. But these are found in very, very small quantity. And I'm not going to expect you to learn all 16 of them, but I can give you a couple of examples. So one of them they give you is iodine. There is only one group of cells in one gland that need iodine in your body. Where is it? There is only one group of cells in one gland in your body that needs iodine. No other cells use it. Your thyroid. Okay, so your thyroid, if you don't know where your thyroid is, because I mean, maybe you've had AMP, maybe you haven't, but if you haven't had it, so if you feel for your Adam's apple, so when you swallow, you feel that little bump that bobs up and down, that's the larynx. Just below and to either side is this soft gland. There's two little lobes. They're connected by a little bridge called an isthmus. But those two little lobes are where all the iodine that you eat goes. No other cell in the body wants iodine. No other cell in the body uses iodine. All the iodine that you eat ends up in that little gland. And that little gland does a lot. That little gland is responsible for all your cell activity. So it makes what's called thyroid hormone. Thyroid hormone affects your metabolism. It affects how active your body cells are. All your body cells respond to thyroid hormone. And in order to make thyroid hormone, you need to have iodine because there's actually iodine in thyroid hormone. Okay, so that's what I mean by a trace element. Trace elements have like very specific jobs. They are typically not found throughout the entire body, but instead they're doing very certain things in certain parts of the body. So these have very specific jobs. And oftentimes you just don't see them everywhere. Iodine, thyroid. If you don't get any iodine, your thyroid will begin to swell and you will develop what's called a goiter. So they found this out when people moved from the East Coast, the pioneers, and they started to go across country on little wagon trains, and they settled out in Kansas, God forbid, okay? So they settled out in Kansas, and then all of these people started developing this neck swelling, and it's because what is not in Kansas? There is very little iodine in the diet because most of your iodine comes from seafood, comes from fish, comes from the ocean. In fact, to counter for that, where do they put iodine now? In salt. So when you buy a thing of salt, it's typically iodized salt, and that took care of this problem. So now, if you don't eat fish, that's not an issue. If you don't like shrimp and you don't like any of the ocean types of fishes, that's where most of your iodine came from. So it's not an issue now because we know that you need it, and so just add it to something that everybody uses, so you buy iodized salt. So, another one, fluorine. When you think of fluorine, what do you think of? Toothpaste, that's exactly right, okay? So fluorine, and again, look at that spelling, it's not flourine, it's U-O-R, okay? So it's fluorine. So fluorine has been found, if you add it to the surface of the teeth, it helps to prevent tooth decay. It actually makes the enamel, the surface of your tooth, more resistant to acid breakdown. And what you eat is typically acidic.
So would you do something like eat raw fish or use a lot of salt? What does that do to your body?
So excess amount of iodine doesn't typically cause major problems because it's used in such a small amount. So it doesn't like build up. So it's not one that like gets squirreled away. So excess can get flushed, can get released. But they saw more of a problem with people that got none and then developed the big knots, like the big bumps. They were goiters that they would end up developing. Last one they've got in this list, iron, Fe. Okay, so fluorine's really not used anywhere else. It's really more, it's like it helps to just make your tooth enamel. So very specific job, very specific place. What about Fe? That is what? Iron. And where does it go? It's used to make red blood cells, okay? Pretty specific. So it doesn't like hang out in your skin cells. It's not typically used in the brain, okay? So when you ingest iron, that gets absorbed and it gets sent to your bone marrow. It can get stored in your liver, okay? If it's not needed immediately, you can store it in the liver and spleen, some other places. But when you need it, it gets sent to your bone marrow, and in your bone marrow is where your red blood cells are made. And if you don't get enough iron in your diet, what ends up happening? You black out. You become what? Anemic. Not enough iron means that you make immature red blood cells. You make red blood cells. Their job is to do what? Red blood cells carry oxygen in your blood. So you can think, if you don't have enough red blood cells, then you don't carry very much oxygen. So when you stand up really fast, you start going, oh no. Okay, grab hold of something, I feel really faint. Okay, or you might look at your fingernails and the nail beds are what? They'll be super pale because remember your nail beds are an indication of circulation. So if they're really pale, that shows that maybe there's not a lot of red blood cells floating in the blood underneath. Or you can look like in animals, you can check their gums. And their gums, like puppies that end up have a high worm load, like they have a lot of intestinal parasites, you'll like lift their lips and they'll just be, gums will be white like a piece of paper. You're like, whoo. No wonder you're not running around. And they're like, hey, okay, give them some warmer, give them some food, and 2 or 3 days, they're like, okay, I'm starting to feel better already. Okay, that's why you have to have these trace elements in small amounts because they have this specific job. They're going to serve a very specific role. So red blood cell formation. So those are just some examples, and that's just the main thing, kind of take away from that, not to memorize all of them. So this next slide that they've got actually shows some of them. It doesn't show all of them. Anything that's in the yellow, see the CHM, right? Those are the main elements or major elements. Then they do orange box all of the minor. They didn't list them on the previous page, but they did orange box them the way that they're supposed to on this side. So there's the seven minor elements. And then those micro, they show some of them. We talked about a couple of them. Interesting. Where have you seen zinc and selenium? You have sometimes maybe bought something that had zinc and selenium added. Okay, maybe you haven't. If you ever have a bad cold, you go to the grocery store, you might buy orange juice that has zinc and selenium added. Any idea why? It's in orange juice. What else is in orange juice? There's a lot of vitamin C in orange juice, and it's always been purported that if you have a bad cold, orange juice, vitamin C helps you to get over it, helps to thin mucus. It's really an antioxidant, so it just stimulates cell repair. But they have found that zinc and selenium actually stimulate immune cell response. So next time you have a bad cold, just look for the orange juice that has that zinc and selenium added. That's actually the reason for it, is it helps it increases immune function. It doesn't really change the taste of the orange juice. That's a big kicker. Because those zinc lozenges, those things are horrendous tasting. I'm not a fan. It leaves like a weird metallic taste in the back of my throat. But, I mean, it's zinc. It is a metal. But it's supposed to all help to trigger or stimulate immune system response. Okay? Where are we at? Okay, we're so good. A couple minutes. Okay, so we talked about this. So we're just going to kind of like move through this. Remember that states of matter can be a solid, a liquid, or a gas. Remember that that is going to change how the atoms, how close the atoms come to each other. Changes its volume, changes or its ability to maintain its shape and volume. Here's kind of a chart that like summarizes really what we were talking about when we talked about solids, liquids, and matter. Solids, liquids, and gases. The kinetic energy, the positioning of those particles, its shape and its volume. So it's sort of a review. But now we get to what's known as changes in matter. So we can have a physical change. So a physical change is any kind of change that happens to the substance, but in theory, we could put it back the way it was. Okay, so this example shows ice melting. So you agree that if you take ice out, you can put it back in the freezer after it's water and it'll refreeze. It might not look like, well, back in the day, when I was like, up until 6 years ago, I had ice trays in my freezer. Like my kids' friends would come over and they'd be like, my grandma has these. Like we didn't have an ice maker. I never had an ice maker like up until like I've really come to town in the last 6 years. Okay, so we always just had ice trays, like blue ice trays, you'd crack them. And so same thing, the kids were great. They would always like leave like the single ice cube. The cube below was always left in the tray, just one. Really? You couldn't put more water in here. So you'd pull out 4 with 1 in each. You're like, thanks. Okay, so But if you take that ice, leave it out, because of the change in temperature, the ice is going to absorb energy. The ice will then go through a melting process, become completely water. But I could take and then put it back in the freezer and it would refreeze. Okay? So does it change the water? No. It really changes the vibrational energy of those molecules so that they can pack in tighter together. And then when they warm up, they spread back out and flow. So when you think of things melting, freezing, boiling, condensing, right? So boiling is going from liquid to gas. Condensing is what happens when steam forms on the kitchen windows when you're boiling spaghetti, right? Because the window's cold, so it starts getting all foggy looking. So any of that, those are physical changes. It doesn't change the substance, it just changes the state. Other examples, though, of physical changes is if you bend something, right? So you pull out the saran wrap, tear it off, and it goes. Then you start trying to pull it this way, pull it that way, okay? It's still saran wrap, even if it's laid out flat or if it seems to want to all ball up all on its own. So if you bend, if you roll or stretch, like if you change the shape of a substance, you could take a substance like a carrot. I always think of like a salad. So when you make a salad, it's all physical change, right? So you like chop up your lettuce, rinse it off, throw it in a bowl. Chop up your cucumbers, chop up your carrots. Have you changed the carrot? No, you just changed its shape, right? It's just more palatable than trying to like gnaw on large carrots as you're eating. So it's just changing the shape. So if we're cutting, chopping, pounding, rolling, those kinds of things, changing anything in the shape, but if it's still the same substance, in theory, I could take that carrot and I could like pull little pieces together and it would look like the original carrot, okay? It's got some cuts in it. If you cut paper, any of those types of things, all would be examples of physical change. Just remember, can I change it back? Can I change the temperature and change it back? Could I physically like line them up to change it back? Even putting things through like a paper shredder. In theory, you could like line them all back up and like be able to read what was on the page. All I did was change its appearance, but I didn't change the paper. That makes sense? Okay? But how is this different? So you get your charcoal, you're like, I'm gonna make some burgers. So you get out the charcoal, pile it up, throw down some lighter fluid, throw the match, okay? And you sit and watch it and you're like, wow, fire, cool. Okay? What happens to the charcoal over time? Goes from black to being gray. Okay, so we see a color change that has happened. Over time, does it stay the same size? No. Okay, and eventually, if you don't cover it or anything, eventually, if it completely burns, all you're left with is a small pile of ash. Okay, can I take that ash and like pack it back into charcoal briquettes? That would be nice because charcoal is gotten like stupid expensive. Okay, but no. So those things that you see, one, when I see this color change, and I can't change it back, okay? I can't go back from the gray to the black, okay? Now, there are some things that change color with temperature. You know, like there's those weird cups, you put something hot in and it turns one color, they're cool. But that's a physical change, okay? Chemical change, think, okay, the charcoal briquette starts turning gray. I can't make it go back black. Once it starts turning gray, it's kind of a permanent color change. If you see a substance disappears, and I can't make it come back, okay? If you see heat, flame, if you see fire, if you notice heat being released, if you see bubbles, and the other thing to always think about is, okay, can I, just by changing the temperature or by physically changing the arrangement, can I make these things come back? Okay, can I make it back to the original? And these, like a soda, you open your can of soda, pour it in the glass, it's nice and bubbly. What happens if you just let it sit? It loses its bubbly. Can you make it come back? Okay, so like if the soda goes flat, just putting the lid back on, shaking it a little, is it gonna then automatically recarbonate? No. So carbonation is a chemical reaction, okay? It is where they pump carbon dioxide into the bottle before they seal it. And so that reacts with the water and actually forms carbonic acid. When you break that seal, the reaction of the breakdown of that carbonic acid occurs. So seeing bubbles, seeing a fire, seeing a substance disappear, sometimes something like a smell, like an odor, a gas that may be given off. All good examples. But in 99% of reactions, there are some reversible reactions, but in 99% of reactions, you can't change it back. And that's really the one to think about when you think about trying to identify physical changes versus chemical. So in your head, just ask yourself that question. Okay, I'm gonna quit there. So there is a question in your pre-lecture that talks about balancing equations. It's fine if you missed that one. I've got to kind of alter that one set. If there's any in there that you're like, I couldn't figure that one out, that one will still be okay. But we will do chemical balancing equations on Tuesday, and then we will be able to go into the measurements of matter and doing unit conversions. So do make sure that you bring those handouts back with you on Tuesday, because there's a balancing equations worksheet and there's a unit conversions worksheet then.